Okay, we will start. So today's lecture is the fourth one. We talk about turbulence today. So we have done 3 lectures so far. You have come to your tutorial classes, some of you. How are you doing with your assignment? Under control, yeah? They should be fine. Regarding the assignment, so the different students asked various questions, so I'll summarize some of them. Like, okay, the basic exercise is for you to do a simple pipe flow simulation, just like in your tutorial. Use a fluid of your choice. Don't take a non-Newtonian fluid or a complex one. Just use something like air, water, or an oil. Okay, so and then you are supposed to do the T-Junction. Make sure that you have a nice grid for that, a good grid that have enough grid resolution at the volts and at the bend, as well at the junction rather. Okay, so make sure you do that. And some asked whether you need to change the fluid. Well, it's okay to change the fluid. You can compare a couple of fluids if you want, but make sure that you do your basics right. Just simulate both with either air or water or the fluid of your choice. Make sure you get the density right, make sure you get the dynamic viscosity right, make sure you reference that to something, some information that you found from your literature survey. Okay?
I've got a question about the T-Junction.
Yes.
So you asked in this assignment to compare it to some empirical calculations. So are you talking about velocity calculations? Or
Yeah, there are simulations out there which you may be able to find. So just compare your results with results that other people have done. We are only worried about the velocity and pressure fields. Okay, we'll look at turbulence today. So you know what is meant by a laminar flow, and you also know what is meant by a turbulent flow. But we will look at how turbulence is treated in CFD. Sorry. We will look at how turbulence is treated in CFD. What is turbulence and why turbulence is important? And we will talk about what is called the Kolmogorov Energy spectrum. And then we will look at the methods of predicting turbulence in CFD. We have what we call direct numerical simulation. We have what we call large eddy simulation, and then we have Reynolds average Navier Stokes simulation method. Okay. When I was studying, when I was reading for my postgraduate degree, so I had a German friend. His name was Matthias, and his parents asked him, "What do you do? What do you do?" Then it was in the summer. They were sitting out, and he showed the sky and said, "Well, I'm modeling that." He was doing large eddy simulation modeling, and if you were to model the clouds, the flow of air and the clouds, you would not use just large eddy simulation. you use what is called very large eddy simulation. Okay. So we'll talk about that at some point. Okay. Turbulence happens because of two things. One is the velocity of the flow, and the other is the eddy formation. Eddy formation is due to the viscosity of the fluid. Okay. So if the fluid is not viscous at all, there won't be eddies forming. It will flow like it will flow without any disturbance. Okay. But that doesn't happen. So there is viscosity in the fluid. Therefore, eddies form. Good examples are, when you have a large mass of water, like a large river or the sea, you always see that air flows over the surface, and there will always be waves. Okay. Those are examples of eddies, how eddies can be formed. Okay. Because when you have a plane surface of water, when air flows over it, because of the friction between the air and the water, some of the water will be carried away will be moved by that air, and because of that it carries it sweeps some of the water, and when it sweeps the water, the height of the water rises a little bit, and at some point it can't hold that amount of water anymore, and it will drop. So that's how eddies. That's how waves are formed. So this is an example how turbulence is initiated or created. And turbulence is random. It's a random process. It varies in time and in a random manner. And in a full turbulent flow, you will have eddies of different sizes. So you have large eddies, you have small eddies, you have very small eddies. Okay, and in turbulence, we say these eddies break up, meaning when you have a large eddy, that eddy will be broken into smaller eddies and further smaller eddies, and during this eddy breakup process, energy transfers, meaning energy dissipates due to the breakup of eddies. So the large eddies will have more energy, the smaller eddies will have less energy. So energy dissipation is through this breakup of eddies. So this is an example of a turbulent jet flow. So it's a jet entering. This is a jet entering a fluid or area. So therefore, you can see that even though this has a regular velocity profile, your flow will become turbulent there. Okay. So these are kind of example problems which you can use. So there are empirical results for these one. So if you can model these type of flows and validate your CFD code. And these are some other examples. So this is a picture of a tip vortex formed by an aeroplane. This is a giant eddy in the atmosphere. This is actually a large swirl there. And in a wind farm, you will always have eddies behind the wind turbine. And this is just a wake of a jet flow, and flow over a hull of a marine vehicle, in this case a submarine, and obviously ocean waves. So I told you how ocean waves can be created. Yeah. So the importance of turbulence is all flows, most flows are turbulent. Okay. Most internal and external flows are turbulent. Okay. So examples are pipes, heat exchangers, pumps, compressors, turbines, and engines for internal flows. And external flows are like wakes of aircraft, ships, trains, cars, different type of balls, etc. And naturally you will find turbulent flows in rivers, lakes, and oceans. Just gave you these examples. So this is an example why turbulence is important. This is not a happy example. This is actually a sad one. So because they didn't account for turbulence during snow formation in an aircraft, a DC-9 taking off during a snowstorm at Denver, it encountered troubles. It stalled and it flipped over, just because they were not they were not expecting the turbulence to happen during the snowstorm. Okay. And there, what happened was vortex air in the wake of the jet landing nearby runway. It didn't dissipate. Therefore, the other currents nudged the plane into the path of DC-9, and the plane flipped over due to the turbulent currents formed by another one. Okay. So you must. I mean, it's very it's common sense to say that when you have a if you have cross paths in a runway, you will have different. You will have unwanted turbulent flow fields. So that's why you see that in busy airports and busy runways, you land and take off in the same path. You don't cross it due to safety reasons, as well as when it is busy, it will run like a straight flow basically. So when you drive near Heathrow from Reading to along M25, you see planes preparing to land one by one after the other. Yes, so they come in the same path basically. So this turbulence in this aircraft was due to the ice formed on the wings. So you want your wings to be really, really smooth. Otherwise, the skin if your skin friction is different due to ice formation, you have more turbulence. So another example is you know racing cars. You want to have a laminar boundary layer formed over the body of the car when in the front, but and it will have a drag. Yeah, there are two kinds of drags. One is due to the skin friction, so you want to minimize that. But when you get to the end of the car, when you get to the end, there will be these streamlines. They detach. Okay? If they detach, what will happen is there will be a vacuum created here. Therefore, what you really want to do is you need turbulent flow here at the back, and in the front you want laminar flow over the body. At the back you need turbulent flow so that your drag from behind is less. Okay, that's why you have in fast cars you find a spoiler at the back. So what that does is that doesn't give you a streamline flow. That will create some turbulence in there. Okay. In the 90s, etc., in the 80s, 90s, you would have seen cars did have tail lights which have grooves on them. So they were not smooth; they had grooves on them. Good example is the Mercedes lights in the 90s before they had more streamlined bodies in the 2000, etc. But that is to create turbulence at the back. Okay, we'll look at what is called Kolmogorov energy spectrum. So in turbulent flows, you have large eddies, big eddies, and then these large eddies are not stable; they break up. They break into small eddies and smaller and smaller eddies, and during this breakup of eddies, it transfers energy into these smaller and smaller eddies, and finally these small eddies dissipate. So thereby you see that the energy that was stored in these large eddies would dissipate through to the small eddies, and it will dissipate. Okay, this is called the energy. You call it the energy cascade as well. And once these eddies are broken up, the energy is lost. Okay. So this energy cascade continues until the molecular viscosity is effective in dissipating the kinetic energy as heat. So what happens is these eddies break up. The large eddies break up to smaller ones, and to smaller ones to the further one, and then they break up when at the end fully break, and there won't be any eddies. At that time, heat is generated due to friction between the molecules. Okay? That's how. So in the turbulent flow, you will always see that heat is generated at the end. Okay. So this is an example of the scale of the structure. So this here the structure is small, where here the structure is really large. So then we need to look at what you call the length scales. Then my example comes. Now if you are looking at the clouds, their eddies are really large. And to encompass or to encapsulate the size of those large eddies, you can have a fairly large grid. Yeah? But if your eddies are really small and if you have a large grid, this grid, the eddy will be within the grid. Yes? Therefore, the grid won't see the eddy. For the grid to see the eddy, your grid size should be much smaller than the eddy size. Yes? Make sense? And then when you look at these eddies, you determine a grid size and say that some of the eddies which are smaller than the grid size will be discarded in your turbulent calculation. Yes, they have to be, because the grid doesn't see the eddies. Okay. Now this smallest eddy size is called a name is given, which is called the Kolmogorov length scale. Now that is the size of the smallest eddy that is that you look at in CFD normally. So the largest eddies are what you call the integral length scale. That means if you have a large eddy, and if your total problem is smaller than the large eddy, if your domain is smaller than the large eddy, no use, is it? Because your domain doesn't contain the eddy. So your domain should be larger than the eddy. And then you have your microscales, which are the smallest scale, and there is the Kolmogorov scale, where you have the practical scale for the eddies. Okay. These are called Kolmogorov scales because Kolmogorov theory, he described the how eddies will be dissipated, how energy is dissipated due to eddies. And he said that smallest eddies are isotropic and they are independent of geometry, obviously, because your smallest eddies are not encompassed within the grid itself, right? And the dynamics of the flow is normally dominated by the large eddies. So it's like if you want to fill if you want, okay, you have a bucket, you have a rock sample containing a lot of elements, large ones, smaller ones, sand and everything. So if you want your bucket to be filled fully with earth, what you have to do is you need to put the largest bulk in first, then the next size, then you fill the rest with sand. Okay. This is true with life as well. You need to sort your largest building blocks of your life first. Okay, so flows are dominated by large eddies. So you need to know the mechanics of the large eddies before you can simulate or analyze the flow. And this theory has been proven correct empirically. Okay. Okay, then we will look at how we predict turbulence in CFD. We have what you call the direct numerical simulation. So in this one, in direct numerical simulation, everything is solved through an equation. You solve the Navier-Stokes equation numerically. Nothing is modeled. You don't assume anything. You just solve it. Okay. And the whole range of turbulence scales must be resolved from smallest the Kolmogorov scale to the largest scale. Yeah. And to accompany this, you need a very fine mesh. Your mesh should be much smaller than the Kolmogorov scale. So because you need to encompass your if your eddy size is that, you need to have at least few grid nodes in that eddy. Okay. So therefore, your grid has to be very small, very fine, not small, very fine. And then it also needs a very small time step. Okay, because to encompass everything. And you need to model transient behavior, and it has to be exact 3D. This is good. All of this is good if you have enough computer power, and if the problem is simple. Okay, and this method is very time consuming. Only good for what you call hypothetical flows or very small problems. So the computational effort is proportional. Computational effort is the size of the computer is proportional to Reynolds number to the power 3. Okay, and this is not suited for industrial applications. We can use the computer power to do this, but to do a proper DNS simulation on even a small scale flow, you need a nice set of parallel computers. Okay. But this is there is a use of DNS, which is now your Reynolds average, Navier-Stokes, and LES are they are made by approximation. So you can test those results using DNS, okay, in a small problem, small representative problem. We'll see whether we can watch one. So this is a simulation of a fairly straight problem. When it you can see when the eddies change when the Reynolds number changes. So it's a fairly regular small grid that you're using for this. So okay. Yeah, you can you can watch these videos when you follow the lecture again on your computer. You click on the link and it will pop up. Okay. In larger simulation, which is the next step in simulating, or next scale larger than the DNS, it solves the large eddies, and the subgrid scale, meaning subgrid means the scale that is smaller than the grid, are not solved. Okay. So mathematically, the velocity field is filtered into a resolved and subgrid part, and the larger eddies are called the large eddies compared to the grid scale, and subgrid part of the velocity is called small scales and represent velocity. And this also requires 3D simulation. It's transient modeling, and it needs a spatial and temporal solution of scales, which is called the internal subrange. So you solve the velocity field first, and then use that velocity field to do the next step in the turbulence calculation. So so LES is the kind of sensible solution between RANS and DNS. So LES can be used in most of the cases, and which is you can also use what you call the very large eddy simulation for really large problems. Therefore, depending on your computer power and depending on your problem, this is a practically used. This is a method that can be practically used. LES, okay. And it has a better accuracy than Reynolds average Navier Stokes equations, and obviously it also has a large computer requirement. And you know by now that you can use okay, you haven't used it, but you can use LES for different kind of simpler problems. Obviously, a large set of data are generated when you use LES. Okay, well, even in DNS you have a large set of data, but in LES you have a larger set of data because you have to store some information before when you do the calculation. Okay. You have to store the velocity field basically. So there are some other examples as well which you can see at your leisure, but I'm not going to show you this. These are just animations of floats. And then what you call you have what you call Reynolds average Navier Stokes equations. So in Reynolds average Navier Stokes equation, it provides a complete description of turbulence. If you want to do that, so what we do is we approximate turbulent terms, and so we do that because for most engineering problems it is not necessary to we don't really need the details in turbulence. We only need to appreciate that it is turbulent, and if you can resolve the flow field accurately enough, that is enough. Okay. So therefore what RANS does is it resolves the mean flow. Okay. So it will give you what you call the time averaged velocity. So because it's transient, or because you have fluctuating velocities all the time, but you still have a average velocity. So what you need is a time average velocity. So what RANS does is it will give you a time averaged velocity field. And when it does that, it saves a lot of work, a lot of time, and a lot of computational power as well. We will see what Reynolds stresses mean. Okay. So in RANS, we use time averaged equations that give conservation equations for the mean values. So it models turbulence successfully, and it does not the answer does not vary with time. Okay. So remember that this is a statistical property of the flow, which means it's not exactly what is happening at a snap at a particular time, but it is what is happening over a period of time. So you can get a snapshot, and the snapshot doesn't change over time in RANS. Okay. So it is not the existing flow pattern. It does not usually satisfy the steady Navier-Stokes equation. The flow doesn't look that way either, but it should be good enough for you to understand what is going on. Okay. So whatever the circumstance, your turbulent model, the turbulence model, must have a wide applicability. It has to be accurate, and at the same time, it has to be simple and economical to run. So you need to weigh between how accurate you want that to be and how much it will take in time, and how simple it is to run. Okay. So in RANS, time averaged equations have 6 additional unknowns in the momentum equation. Now these are the time averaged. So what you do is you write your velocity field. If you say your velocity is u plus u dash, u plus u dash. Okay. U is your mean velocity, is your mean velocity component, and your u dash is the random part. Okay. Your u dash changes, doesn't it? So that's how you define it. So you define u, v, and w, all three the same way. U is equal to u plus u dash, v is equal to v plus v dash, w is equal to w plus w dash. But in the long run, the average velocities should be equal to u, v, and w. Yes, even though the fluctuating component varies over time, that addition of those should be equal to 0. Okay. So therefore, when you define your u, v, and w, you will have additional terms in this form. Yeah. So turbulent model needs to close the system of mean flow equation. So meaning you need to have when you have this set of equations, you have to have a same number of unknowns, and your number of unknowns should be equal to the number of equations that you have to solve it. Yes. So the main task of the turbulence modeling is to develop the computational procedures of sufficient accuracy to solve these equations. Okay. So these flows, turbulent flows, are complex. Therefore, it is solving these unknowns is not straightforward. Okay. Okay. So then we will summarize what we just talked about. So in turbulence, your turbulent flow is irregular with random fluctuations. And we look at the pressure and velocity components, and that vary with time and also in space in a random manner. So therefore, if you, for example, if you plot your u against t, this is what you will get in the actual fact. Yes. So that is your u. In the red line, what you will see is u, and u bar though is the average velocity. Yes. So you can define your u as u bar plus your random component. The random component could be minus or plus. Yeah. So u is defined as the instantaneous velocity component. U bar is the time average velocity component, and u dash is the fluctuating velocity component. Okay, that is u bar, and that is u dash. Yes, and the average of u dash should be equal to 0. That's true. Yes, because your u bar is the average velocity. The average of u dash should be equal to 0. And likewise, your average of v dash and average of w dash should be also equal to 0. Then we will look at how incompressible turbulent flow is. So that's your Navier-Stokes equation, if you remember. So the first term gives you the local acceleration, then the second term gives you the advective acceleration, which is the spatial component, and then you have the body force effects, and the next one is the pressure gradient, and the next one is the other stresses, which is this is the stress component. Yeah. And if you replace your u with u bar plus u prime or u dash, and v with v bar plus v prime or v dash, so v prime and v dash are the same. Okay. So you write this equation, Navier-Stokes equation, like this. Okay. That's your Navier-Stokes equation for the turbulent flow. But because u bar is constant, u dash, if you integrate u dash over time, that should be equal to 0. Therefore, you can get rid of some terms. Yeah. So, for example, this one is if you average that one, you will end up with u prime. Yeah. But your average of u prime times u prime is not equal to 0. Okay. And in Reynolds average equations, now you are not supposed to derive these. Okay, so I'm just trying to explain how these terms are used, right? So by Reynolds averaging, you can, by continuity equation, you can say for W prime, W bar plus O W x plus W V bar O W plus W bar O W Z is equal to 0. Okay. And then you have your this component over here, and then these elements, that one, and that one, are called what you call Reynolds stresses. Reynolds stresses. So this total equation is the Reynolds average Navier-Stokes equation for incompressible turbulent flow in x direction. So you can write this equation like this in y direction and in z direction as well. Okay. So this what you do here is you replace your Navier-Stokes equation with fluctuating and a random component. Okay. A mean component and a fluctuating random component. So you replace your u with u bar plus u prime, and v with is equal to v bar plus v prime. W is equal to w bar plus w prime. And RANDS is the most common method of modeling turbulence in CFD. There are various expressions for approximating Reynolds stresses. Now, these are the Reynolds stresses. Okay. And in Reynolds average Navier-Stokes method, you have few models. So what you do, there is a zero equation mixing length model. There is a one equation model, and there is what you call a two equation models. Those are the ones that we used in our calculations. So K epsilon model, standard RNG or realizable K omega model. So these are two equation models. Okay. And then again you can have a 7 equation model where you resolve the Reynolds stress completely. That is a Reynolds stress model. So when the number of equations increase, you have the number of partial differential equations that you need to resolve increase as well. So that means this model here is more time consuming than these models. But for the general flow, like in your pipe case or in your T-Junction case, your Reynolds, your K epsilon model is good enough. And somebody asked this question once. Okay, are we using RANDS? Yes, we are using RANDS. Are we using RANDS in the in the tutorial problems? Yes, we do. We are, and we are using it with normally K epsilon model. That's what I asked you to do. But you can try the K omega model if you want. Okay, so we will stop at that for today. So next week we will have the last theory lecture, and then in January we will have a revision class as well. Yeah, January first academic week. Yeah. So all doing well with the tutorial assignment. You should have enough computers now, so the arrows have finished the assignment.